For these equilibrium calculations, the answers are provided for you on the worksheet. This video is provided in order to give you some help getting to the answers if you don't see them. So we'll start with number 1. What is the equilibrium constant expression for this reaction? Remember that solids do not appear in the equilibrium constant expression. So the Kc will be equal to the concentration of the hydrogen raised to the 4th, because that is the coefficient in the balanced chemical equation, divided by the reactants. In this case, we have water. Now, water will be raised to the 4th as well, the concentration of water. Usually we don't have water in the Kc expression, but this is a gas. We don't have liquids and we don't have solids. That's where water doesn't come into the Kc expression. So for B, if this equation has this equilibrium constant, 2.4 times 10 to the negative 7, then what happens if we're going to multiply all of the coefficients by a third and then switch the order? Well, what happens to the Kc in this case is we're going to take the cubed root, because we are taking the original Kc, which is what this is, and it would be NO squared Cl2 times the concentration of Cl2 divided by NaCl squared. And what we're doing is we're transposing that, we're translating it into the upside down, and we're changing the coefficients. So you have to recognize what's happening to the Kc in this case. So the first thing I'm going to do, that's a 1/3. First thing I'm going to do is take the cubed root of my Kc. Then I'm going to put 1 over top of it. So the cubed root of, let's see if I can get my calculator here, 2.4 times 10 to the negative 7. We get a cubed root of 6.214, and I'm going to leave this number in my calculator, times 10 to the negative 3rd. Now I need to switch it. I need to turn it upside down. So I take the reciprocal, that's 1 over this value. And when I do that, I get 160, which can also be shown as 1.6 times 10 to the 2nd, and that's shown with 2 significant figures because the original Kc value had 2 significant figures. So for C, given these equilibrium constants, what's Kc of this reaction? Well, this is similar to Hess's law, but here we're going to be applying it to K's instead of delta H's. So you have to notice how these equations are being added. Because we are adding these 2 equations together, what we're doing is we're going to multiply our Kc's. When we multiply these Kc's together, so that's 6.1 times 10 to the 8th, and we're going to multiply that by 1.2 times 10 to the 14th, then I get 7.3 times 10 to the 22nd. And that is the new Kc for this reaction, built from the parts. Number 2, if we have this mixture, and we have 9.22 moles of A and 10.11 moles of B, 27.83 moles of C, and they're all placed in a 1-liter container, then our moles are our concentrations, our molarity. So the reaction is allowed to reach equilibrium, and at equilibrium, the number of moles of B is 18.32. What's the equilibrium constant for this reaction? The first thing we do is notice that B is increasing, and it's increasing by some amount 2x. Now I know it's increasing because I'm given the equilibrium value and it's greater than my initial value. That means A is also going to be increasing, but it's going to increase by some value of x. I know B is going to increase by 2x because of the 2 in front of B for the balanced chemical equation. That means C is decreasing by some amount 3x. Now I'm going to need all of that information, but first I'm going to calculate what is my x. So I'm going to set my 10.11 plus 2x has to be equal to my equilibrium amount of B, 18.32. And then with just a little bit of simple algebra here, I can solve for my x, which I end up getting 4.105. And I'm leaving that value for now. I understand that those are incorrect significant digits, but I am leaving that value for now. Then I'm going to calculate my equilibrium values of A and C. So 9.22 plus 4.105, that's going to round to 13.33. And for C, 27.83 minus 3 times this value, 4.105, I end up with an equilibrium. So this is my initial change in my equilibrium. I forgot to put the ice in. So my equilibrium value of C, 27.83 minus 3 times my X value, I get 15.52 for my C value. So now I can put those values into my KC expression. Well, the KC expression is going to be the cubed value of C divided by the concentration of A times the concentration of B squared. All I have to do is fill in these values. Make sure you enter it into your calculator correctly, and you should get a KC value of 0.836. Number 3, at a certain temperature, the KC value is given for you. So we have our initial or change in our equilibrium. We're going to need that. We don't know what the initial concentration is, but we do know that it's going to change by 2x. And we know that because we're told we've only added the IBR to establish the equilibrium. So we're going to subtract some amount 2x, but we're going to add that some amount x in order to find our equilibrium concentrations of everything. So our equilibrium concentration of IBR is going to be the initial concentration minus 2x, but we're told what that is, and that is equal to 0.0124. But how does that help us? Well, we will use that at the end, but first we need to calculate what our KC, what our X value is going to be. So KC is equal to 4.13 times 10 to the minus 2. It's also equal to the concentration of the iodine at equilibrium times the concentration of bromine at equilibrium divided by the concentration of IBR squared at equilibrium. Well, I know what the concentration of IBR is at equilibrium, and it's 0.0124. But I don't know the concentrations of my I squared and my BR squared. Or not squared, my iodine and my bromine. And those two values are x's. When x multiplied by x is x squared. So this is the value I have. Now with just using algebra, you know what? I need to square this value as well. Multiply 4.13 times 10 to the negative 2 by 0.0124 squared, and you should end up with x squared is equal to 6.35 times 10 to the negative 6th. So the x value, take the square root of both sides, is 2.52 times 10 to the negative 3rd. And that's fantastic, but that doesn't answer the question. We need to keep going. Now this is the concentration of iodine, and it is the concentration of bromine at equilibrium. But that does answer the question. That answers the first part of the question. I'm ahead of myself. Now the next question is, what's the initial concentration of IBR before the equilibrium was established? Well, Mi minus 2x is equal to 0.0124. Now the only part we don't know is that Mi, because x is 2.52 times 10 to the negative 3. So with just a little bit of algebra, you should be able to find out that the initial concentration then is 0.0174 capital M molarity. Number 4, if we have 0.924 moles of A placed into a 1 liter container where it's 38.8% dissociated when equilibrium is established, then what is the value of the equilibrium constant at the same temperature? Well, in order to start this, I'm going to start with my 0.924 moles of A. And it is 38.8% dissociated. That means 0.388 of it has been reacted. So 0.924 times 0.388 is 0.359 moles of A have reacted. Well, initially, we have 0.924. It's going to change by some amount x, and actually by 3x. B is going to increase by 5x, and C is going to increase by 2x. Well, in order to find out how many moles then we have, we can take that 0.359 moles of A, and we can solve for x. So this is equal to 3x. So then x is equal to 0.120 moles, or molarity. We're in a 1 liter container. So now we can find out what our equilibrium values are. So 0.924 minus our 0.359, what we reacted with A, we have an equilibrium value of A of 0.565. All I did was take the initial concentration and subtract what reacted, this 0.359. Now to get B, I'm going to take 5 times my x value. So 5 times 0.12, and I get a value of 0.600. This value may drift a little bit if you have not rounded. In fact, the first time I did this problem, I got 0.598. So there could be some rounding error associated with these values. So then I have 0.240 for my concentration of C. Again, the first time I did it, 0.239, because I did not round any of my answers until the end. So the Kc value is then going to be B raised to the 5th C squared over A cubed. So I fill in my values. And I calculate. So 0.6 raised to the 5th times 0.24 squared divided by 0.565 cubed, and I get a value of 0.0248. Now again, you will notice some drift in your numbers if you don't round. Initially, I did not round this value to do any of my calculations, and I ended up with a Kc value of 0.0241. If you show me your work within the classroom, this kind of drift is insignificant if I can see your work. Number 5, the equilibrium constant is given to us as 2.60 times 10 to the negative third. If 0.820 moles of our reactant, and then we have an initial amount of each of our products are mixed together, what are the concentrations at equilibrium? Well, let's see. First thing I need to do is calculate my Q value, because I need to know which side is going to be added to and which side is going to be removed. So my Q is going to be similar to my K value. I'm going to take the concentration of my products and divide it by the concentration of my reactants raised to the appropriate powers. So in this case, we're mixing in a 1 liter container. That makes everything so much easier when calculating. So I have my 0.223 for each of my products, and then my reactant is 0.820. So to calculate this Q value, you take 0.223 times 0.223 and divide it by 0.820 squared. And I get a value of 7.40 times 10 to the negative 2. Now my Q value is greater than my K value. That means the reaction is going to shift to the left. So we're going to subtract from the product side and we're going to add to the reactant side. And that is because my Q is greater than K. We need to make this value smaller, and we do that by reducing our products and increasing our reactants. So initially I had 0.820 here, 0.223 and 0.223. I put these in order of the chemicals as they are given right here. And then we're going to change, and we're going to change by some amount. It's stoichiometric. And we are adding to the reactant side, so we're adding a 2x here, and we are subtracting x's here. So my equilibrium concentrations, 0.820 plus 2x, 0.223 minus x, 0.223 minus x. Now I'm going to show you a way to do this without the quadratic equation because there's no reason to make this extra hard. So our k is going to be equal to, I'm just going to start filling in the numbers. We're going to have 2.60 times 10 to the negative third. And that's going to be equal to 0.223 minus x times 0.223 minus x. And I'm going to divide that by 0.820 plus 2x, and that is squared. Now, here is a little tip. If we take the square root of both sides, we can avoid the quadratic equation in this case, because the square root of 2.6 times 10 to the minus third, we have 0.0510, and the square root of this business here, well, we just take 0.820 plus 2x and 0.223 minus x. So we can avoid the quadratic equation here. Now we just have some algebraic stuff that we need to do. Multiply both sides by the denominator. I end up with 0.04182 plus 0.102x plus, equals 0.223 minus x. Get your x's on one side, get your constants on the other side, and get 0.8118 is equal to 1.102x. Solve for x, and I get an x value of 0.164 capital M molar. Now, that is not the answer, though. We need to keep going. So this is my x value. What are the concentrations? Well, the concentration of N2 is going to be equal to the concentration of O2, which is 0.223 minus 0.164. And that value is 0.059 capital M molar. So those are the concentrations of N2 and O2. The concentration of NO, on the other hand, is going to be 0.820 plus 2 times x, which is going to be 1.15 capital M molar. So now let's start. If we have 1.16 moles of A, 1.35 moles of B, and 0.641 moles of C in a 1 liter container, so these are also our molarities, and we're allowed to reach equilibrium, then we're told, because we have for our equilibrium 1.95 moles of A. So here's my initial and here's my change. So I must be adding 2x for my change here, which means I'm going to subtract 2x from B, and I'm going to subtract x from C. So we need to calculate this equilibrium constant Kc. So 1.16 plus 2x is going to be equal to 1.95. Subtract 1.6 from both sides, then divide by 2, and I get an x value is equal to 0.395. Now, when I calculated this, I ended up taking 0.40 because we only have our 2 digits after the decimal places here. Not sure that was wise, but that's what I did. So we can calculate our equilibrium concentration. So 1.35 minus 2 times my x value. I end up with a value of 0.55 here. And for C, 0.641 minus x, I get 0.241. So now I can calculate the Kc, which is going to be B squared times C over A squared. So I insert my values and I do the arithmetic. So 0.55 squared times 0.241 divided by 1.95 squared, and I get a K value of 0.0191, or about 0.019. Number 7, we have another one of those partially decomposed problems. And when we have a partially decomposed problem, so we're going to start with what we're given. We have our 0.822 moles, and it's partially decomposed, and it's decomposed at 36.7%. So I'm going to multiply 0.367 by my initial concentration, 0.822, and find out how much of this stuff has been reacted. So I have 0.30, and then I end up rounding to 2. So that's how many moles of SO3 has been reacted. Now, initially, I have 0.822, and I'm going to change it by some amount to x. Well, this amount to x is equal to 0.302. So I can solve for x. And x is 0.151. So our amount of SO2 is going to increase by some amount 2x, so that's going to be equal to my 0.032, and it will also, my concentration of O2 at equilibrium will be equal to x, which is 0.151, capital M, molar for all of these. So the SO3 concentration at equilibrium, I take my 0.822 and I subtract the amount that has reacted, 0.302, and I get a concentration of 0.520 at equilibrium. So now I can put all of these things into the Kc expression, which would be SO2 squared times O2 divided by SO3 squared, and I use those equilibrium values in order to calculate the Kc. So 0.302 squared times 0.151 divided by 0.520 squared, and I get a value of 0.0506. You could also call this 5.06 times 10 to the negative 2. Either way, you're saying the same number. For number 8, we have our equilibrium constant given to us as 0.143, and we're told that we have introduced 1.34 moles of each of our products. But we have 11 liters this time. So we need to convert this into molarity. Now, when I did this initially, I did not leave this number in my calculator. I do strongly recommend that you do so. I think you get a more accurate representation, or more precise, to be thorough. So this is my initial concentration. We're going to change by some value. So I'm going to be adding 2x to BRCl, the reactant side, and I'm going to be removing x from the product side. And then I will find the equilibrium concentrations. So I'm going to give you this value that I have here. 0.122 is what I used. And we need to set this up into the Kc expression. So we have our concentration of Br at equilibrium times the concentration of Cl2 at equilibrium divided by the concentration of BrCl2 squared. And that's going to be equal to my value 0.143. Now, typically, we would end up using the quadratic equation, but we don't have to make it hard. We can take the square root of both sides. That's okay. So if we take the square root of both sides, then I have 0.378 here, and that is going to be equal to 0.122 minus x over 2x. So now I can just use my algebra, and I find by multiplying by 2x on both sides, and then collecting my x's and collecting my constants, I find that x is equal to 0.0695. So now I can calculate my concentrations. And I calculate the concentration of my bromine and my chlorine. They're going to be equivalent at equilibrium as 0.122 minus my x value, which is 0.0695. So the concentration of bromine and chlorine at equilibrium is 0.0523 molar. Now the concentration of my BrCl, on the other hand, is going to be equal to 2 times my x value, 0.0695. So I have a concentration of 0.139 molar. Number 9 is working a little more of that Hess's law algebraic gymnastics. So we have our this is the equation we're looking for, and this is what we're comparing it against. Now, the difference between these two equations and the coefficients is a multiplying by 3. So initially, if I multiply this one by 3, I'm raising my Kc value to the cubed power. But I also have it flip-flopped, and because I have it flip-flopped, I need to take the reciprocal. So I want to take the reciprocal of my Kc value cubed. And when I do that, I get a value of 2.3 times 10 to the 16th. For B, if we're going to write the equilibrium constant expression for this reaction, remember you do not have solids in the Kc expression, so it's just going to be your products over reactants. Your carbon monoxide, CO, is going to be squared, as is your carbon dioxide, because they both have a 2 in front of their respective chemical formulas in the balanced chemical equation. And number 10, for this reaction, the Kc value is given as 42.5. If a half mole of NO2, so we have initial concentrations, and let's see, oxygen, 0.122 mole O2, and then we have 0.300 moles of NO3, and we're mixed in a 1 liter container, so these are also our molarities. In what direction will the reaction proceed? Well, we need to calculate our Q value, so that's going to be NO3 squared over the product of NO2 squared and O2. So we fill in the values that we know. And we calculate our Q value. This Q value is 295. Because Q is greater than K, we need to shift this so that Q decreases. In order to get Q to decrease, we need to remove product and make reactant. So this will shift left towards the production of reactant.